Hello class, today we're going to go over section 4.2, combining functions and composite functions. Now our objectives today are to find the sum, differences, products, and quotients of two functions, form average cost functions, find the composition of two functions. Now we'll have a couple operations we'll go over. We'll go over sum, difference, product, and quotient. Now for the sum, we're just adding two functions together. F plus g of x equals f of x plus g of x. So we're basically breaking these two down into individual functions. So if we have an example with f of x equal the square root of x and g of x equal x to the third, if we're just simply adding the functions, we're just adding what the functions are. So we're adding the square root of x plus x to the third there. Oops. Now, if we're subtracting, we're essentially doing the same thing. F minus g of x is the same thing as the whole f of x function minus the whole g of x function. And if we take the example with the square root of x and x to the third, we're just subtracting x from x to the third from the square root of x. We've got square root of x minus x to the third because we're just subtracting the two functions. Now with product, we're multiplying the two functions. So f times g of x is the same thing as f of x times g of x. So I'm just multiplying the f function, which is the square root of x, times the g of x function, which is x to the third. And you can even rewrite it as x to the third times the square root of x if you want to. Okay. If we're looking at a quotient where we're dividing here, we have f over g of x is the same thing as the f of x function divided by the g of x function. We just have to keep in mind that when we divide by the g of x function, we can't let that g of x function be 0. So if we use our little example over here to the right, f over g of x equals the square root of x over x to the third. And just keep in mind that that g of x function can't be 0. So in this case, that means x cannot be 0. Try some examples. This one says if f of x equals x to the third and g of x equals x minus 1, find the following functions and give their domains. So we have f plus g of x for a. So since f plus g of x is the same thing as f of x plus g of x, I'm just adding the f of x function to the g of x function. So I'm adding x to the third, which is the f of x function, to the g of x function, which is x minus 1. Simplify if possible. Here, there's no further simplification, so I'm done. Now, let's look at the subtraction of the two functions. So if I have f minus g of x, it's the same thing as f of x minus g of x. I just take the f function, subtract the g of x function. Okay, so I'm taking the f of x function, which is x to the third. I'm subtracting the g of x function, which is x minus 1. Just have to keep in mind that this negative does go to all terms in that g of x function. So when I simplify, it looks like x to the third minus x plus 1. Okay, and our domain there is all real numbers. Let's look at C. C is f times g of x, or f of x times g of x. Okay, so I'm taking my f of x function, which is x to the third, I'm multiplying it times my g of x function, which is just x minus 1. I do have to distribute here and simplify. So x to the third times x is x to the fourth. X to the third times negative 1 is negative x to the third. Simplified it down, and the domain here is all real numbers. Okay. I'll look at f over g of x here. I'm looking at f of x over g of x. Keep in mind that f of x is x to the third. G of x is x minus 1. Okay, if I could simplify, I would. Here I can't. The only thing I have to keep in mind is that g of x cannot be equal to 0, which lets us know that x minus 1 cannot be equal to 0, which means that x cannot be equal to 1. That's how they get the all real numbers except 1 clause here for our domain. Now let's look at a revenue cost profit example. It says the demand for a certain electronic component is given by P of x equals 1,000 minus 2x. Producing and selling X components involves a monthly fixed cost of $1,999 and a production cost of $4 per each component. Let's write the equation that models the total revenue and total cost as functions of the components produced and sold in a month. Now the revenue is given by the product of p of x, which is 1,000 minus 2x and x. Okay, p of x function was given to us. All I have to do to find the revenue function from that lowercase p of x function here is multiply it times x. Now, that's essentially just a multiplication of two functions, just like what we just did. So r of x equals p of x times x. So I'm looking at 1,000 minus 2x times x. And all I really have to do here is distribute this x to both of these pieces, and it simplifies down to 1,000x minus 2x squared dollars. That is my revenue function. Now, the total monthly cost is the sum of the variable cost and the fixed cost. So if we change into our cost function here, what's going to cost us to produce whatever this electrical component is, it's made up of two things. Okay, it's made up of a fixed cost, which is something that stays the same pretty much month to month, as well as a variable cost. Okay, and the variable cost here is made up of this additional $4 for each component. So we might not make the same amount of components each month, so that cost could vary. We might make 100 units one month, we might make 2,000 units the next month. Who knows, right? Okay, so our 1,999 is made up of our fixed cost. We add that to our variable cost, which is 4x. Okay, so 4x, $4 for each component x. Okay, and that gives us c of x equals 4x plus $1,999. So now we have our revenue function and we have our cost function. Now let's write the equation that models the profit function as a function of the components produced and sold during the month. Now keep in mind here that monthly profit is the difference between the revenue and cost functions. You have your revenue, which is the amount of money you pulled in and made. You subtract your cost, which is the cost that it costs you to make that money. And then you'll have your profit, what's left over at the end. So p of x equals r of x minus c of x. Now we already have the r of x function and the c of x function. We found both of those. So we just have to input those in their respective places. Here, r of x is 1,000x minus 2x squared. So this is our r of x function here. And our c of x function is the 4x plus 1,999. Now, just subtracting those two functions, the key thing to keep in mind here is when I subtract here, I have to distribute this negative to both of these terms. So I'm really looking at 1,000x minus 4x, which gives me the 996x. I keep the negative 2x squared out front, and then I'm subtracting 1,999. And that's how I get my final profit function of negative 2x squared plus 996x minus 1,999. Now, let's find the maximum possible monthly profit. Now, we could do this by using the formula here, okay? So we could say that the maximum monthly profit occurs at negative 996 over 2 times negative 2, okay? Essentially, all that is, if you look at it, is that's negative b over 2a, okay? Negative b over 2a, right? Because this is your b and this is your a. So that is essentially negative b over 2a. And then if we find that, we can find the resulting profit by plugging that 249, which is what we get out of there, in. And our monthly maximum profit here is $122,003. Now, like I said, you could do that by hand, calculate that. That's fine. Or you could do it on your calculator. I'm going to show you how to do it on your calculator here really quick. Now, if you're doing it on your calculator, you're going to want to use this particular function. Okay. So what you're going to do is you're going to go to y equals, and you're going to type in that negative 2x squared plus 996x minus 1,999. So we're going to go negative 2x squared plus 996x minus 1,999. Okay. If you graph it, it doesn't show up very well on a regular zoom. If I go to zoom fit, it still doesn't show up that well. I need to zoom out from here until I can see the maximum point. Okay, maximum point is going to be in here. I can use my second trace maximum function here, and I can bound it on the left, bound it on the right, and then guess it in the middle and hit enter an additional time. It tells me that my maximum here is at 249 for my x and 122,003 for my y. So essentially finding it and getting the same answer with my calculator as I did by calculating it by hand here. All right, now let's look at average cost. When we think average, right, we add something up and divide by the total number that we have. Now, Sunny's greenhouse produces roses, and their total cost for the production of X hundred roses is C of X equals 5 or 50X plus 500. We want to form the average cost function. Now, all we have to do to form the average cost function is essentially divide by X, which is the total number of production that we have. Okay, so the average cost function is the quotient of the cost function C of X, which is, in this case, 50X plus 500, and the identity function I of X, which is X. So essentially, C bar, which stands for the average of the C of X function here, is just 50X plus 500 over X. All I did was divide the cost function by X, the total cost by the number of items that were produced. Okay, in this case, we're talking about roses. Now, once we have that, it says for what input values is C bar defined? Give a real world explanation of this average. Now, the average cost function is defined for all real numbers such that X is greater than 0 because we're producing roses here, right? Okay. So it's not going to make sense to produce a negative number of roses. So X here has to be greater than 0. It also can't be 0 because if you look back at our average function here, we're dividing by an X and I can't divide by 0. That's why X has to be strictly greater than 0. It says because producing negative units is not possible and the function is undefined for X equals 0. This is reasonable because if nothing is produced, it doesn't make sense to discuss an average cost per product unit. Okay, so we're basically just looking at positive values of X. Okay, now we want to graph C bar for 0 to 5,000 roses, or 50 units in this case. We're going to use the 50 units, right, because we're looking at hundreds of roses. Okay, so I need to divide that 5,000 by 100. That gives me the 50 units that I'm actually looking at. What can we say about the average cost? Now, you can see the graph function here, but I want to actually take you through how to input this on the calculator, okay? So we are graphing the C bar function. So if I pull up my calculator, I'm going to do 50, I'm going to put it in parentheses, do 50x plus 500 divided by x. Okay, if I graph that, I'm going to do zoom standard here. The zoom's not looking that great. That is why they let you know that it's from 0 to 5,000 roses, or in this case 50 units. Because what I can do, knowing that information, is I can go to my window and basically graph it from the x min of 0 to the x max of 50. And then I can do a zoom fit based on that restriction, and it gives me a pretty decent looking graph. Okay, so I took the restriction from 0 to 50, I put that in my window here at my x min and my x max, and then I did a zoom fit. You can just hit the 0 button, but I did a zoom fit here. It basically kept the x constraints and zoomed to fit it on the y-axis so we could see it on that particular range. Okay, essentially this is what it looks like here. As the number of roses increases, so x is the number of roses, as the number of roses increases, the average cost decreases. Now, we have combined some functions. Now we're going to look at the composite function itself. Now, the composite function f of g is denoted by f with this little circle that stands for of g and is defined by f of g of x equals f parentheses g of x, essentially inserting that g of x into the f of x function. The domain of f of g is the subset of the domain of g for which f of g is defined. The composite function g of f is defined by g of f of x equals g of f of x. Okay, so we can go both ways with this. The domain of g of f is the subset of the domain for f for which g of f is defined. Now, let's think about this in a practical term and see if we can kind of understand the mechanics of what's going on here. Now, a composite function machine can be thought of as machine within machine. The composite function machine in which the input is denoted by x, the inside function is g, the outside function is f. The composite function rule is denoted by f of g, and the composite function output is symbolized by f of g of x. Note that for most functions f and g, f of g is not equal to g of f. Okay, so just because you can switch the order doesn't mean you get the same result. Let me show you what I mean by that. Okay, if we look at the basic picture here, we have this input x. It's going through the g of x function first, and then whatever's output from that is then forced through the f of x function to get the total output of f of g of x. Now, if I put it into kind of a practical thought process here, I'm going to use an example with composition and orange juice. So there are two machines in a room. One of the machines squeezes oranges to make orange juice. The other is a canning machine that puts orange juice into cans. Now, thinking about these two processes as functions, we name the squeezing function G and the canning function F. Okay. We want to describe the composite function F of G of orange. And then we want to describe the composite function G of F of orange. And then we want to decide which function G, F of G of orange or G of F of orange, neither or both make sense in the context. Let's start with the first one. Process by which the output function F of G of orange is obtained is easiest to understand by thinking from the outside in. Think of the input as an orange. Okay, that's essentially what we're putting in here. First, we've got to put it into the G. Okay, so when we put it in the G machine does the squeezing. Okay, the output of G will be liquid orange juice that is then put into the F machine, which then puts it in a can. The result is a can containing orange juice. The process kind of makes sense, right? Now, if you try to reverse that and find G of F of orange, what you would first be doing would be putting the orange into a can, or into the F machine, which puts it in a can, and then you would be putting that can of orange into the squeezing machine of G, and the result would be a compacted can containing an orange, which really doesn't make much sense here. So, as can be seen from the results of A and B, the order of the functions appear in the composition function can make a difference. The process that makes sense is the one in part A, putting the orange in the squeezing machine, getting the juice out first, and then putting it in the can, rather than putting the whole orange in the can and then squeezing the can, right? Sometimes it can work both ways. Sometimes you can put it in one side and put it right back out the other. Sometimes not so much. Sometimes order does matter. Let's look at some mathematical examples. So it says for the following composite outputs, using f of x equals 2x minus 5 and g of x equals 6 minus x squared and h of x equals 1 over x, we want to find h of f of x, which is the same thing as putting the f of x function inside of the h function. Okay, so the f of x function here is 2x minus 5. I'm going to put that inside the h of x function here, right? Which essentially just means putting it right there where that x is. So looking at it, h of 2x minus 5 is the same thing as 1 over 2x minus 5 because I'm putting that f of x function in where this x is here in my h of x function. I simplify if possible. Here I can't simplify, so I'm done. Now, let's find f of g of x using the same functions here. Okay, so here I'm basically putting the g of x function now, the g of x function into the f of x function, right here where this x is at. Okay, so I'm going to force this whole thing here in where this x is at. So I'm really looking at f of 6 minus x squared. Like I said, I'm forcing that 6 minus x squared into that x that was in that f of x function. So it should look like 2 times 6 minus x squared minus 5. So the 6 minus x squared going right in there where that x is in this f of x function. I do have to simplify from this point, okay? So I do need to distribute the 2 to both the 6 and the negative x squared. So I should get 2 times 6 is 12. 2 times negative x squared is negative 2x squared. Minus 5, you still have to keep that minus 5 going on the outside. I combine the 12 and the 5 here. I get positive 7, and it simplifies down to negative 2x squared plus 7. So f of g of x here is negative 2x squared plus 7. Now, we want to find g of f of x. Okay, remember on the orange juice example, not always the same thing comes out the end. Okay, so we want to see if putting it in to one side with the f of g of x is going to turn out to be the same thing here as putting it in the other side, g of f of x. We're still going to get a result here. Just might not be the same result we got initially when we did it the other way. So if we find g of f of x here, putting the f of x function in this case, which is the 2x minus 5, in for the x in the g of x function. Okay, so we're putting the 2x minus 5, so g of 2x minus 5, in for the x in that g function. So it looks like 6 minus 2x minus 5 squared. Now keep in mind when we do this that we have to square that 2x minus 5, right? So essentially means we're going to have to FOIL it out. So I'm going to do 6 minus 2x minus 5 times 2x minus 5. Then you can FOIL this out. 2x times 2x is 4x squared. 2x times negative 5 and negative 5 times 2x both give me a negative 10x. If you add them together, you get the negative 20x. And then if I do negative 5 and negative 5, it gives me the positive 25. Now, we simplified it up to this point to 6 minus 4x squared minus 20x plus 5. I do have to distribute this negative to all three of these pieces. Okay, so I'm looking at 6 minus 4x squared plus 20x minus 25. And then I can combine the 6 and the minus 25. It simplifies down to a negative 19 here. So I'm looking at a final answer of negative 4x squared plus 20x minus 19. And if you notice, your g of f of x is not the same thing as your f of g of x here. They resulted in two completely different functions. Now, let's look at a technology note here, because we have the TI-84 that we use in this particular class, and we can take advantage of it to help us in some scenarios with these compositions of functions, even the addition and subtraction of functions, as well as the multiplication and division. But in this case, I'm going to look at the composition of functions with it. So it says if you have two functions, input is y1 and y2, you can enter the sum, the difference, product, quotient, or composition of the two functions in y3. These combination functions can then be graphed or evaluated for input values of x. So this one says if f of x equals the square root of x minus 5 and g of x equals 2x squared minus 4, let's first graph f plus g of x using the window negative 110, 0, 200. Okay, the way we start this is we start by just graphing the functions. So I'm going to let f of x be y1. So I'm going to go y equals, figure out the original y1 here, and I need to input the square root of x minus 5. So second square root of x minus 5. Then in y2, I'm going to input my g of x, which is 2x squared minus 4. Sure, I read that right. 2x squared minus 4. Yep. 2x squared minus 4. Okay, so my f and my g are now entered in here. Now, keep in mind that my f of x I'll let be y1, my g of x I'll let be y2. And we want to graph f plus g of x. Okay, so what I'm going to do is I'm going to let y3 be y1 plus y2. That will essentially be f plus g of x. So if I come over here to my calculator, go down to y3, I'm going to hit alpha f4, y1 plus alpha f4 or trace y2, and I've added my f of x function plus my g of x function now. Okay, I do want to graph on a very specific domain here. My domain is negative 1 to 10 and then 0 to 200. So if I go window, I need to change that from negative 1 to 10, and then on my y I'll change it from 0 to 200. So I've updated my window. Now I can just hit graph. And I have all three functions graphed here. The blue function is my f of x function. The red function is my g of x function. The black function here is my f plus g. Okay. The good thing about this as well is if you hit second graph, you can look at the table here and you can go to specific x values for whole numbers here and see some of your results. So you can see your f of x values, your g of x values, and then your f plus g of x values here. Okay, notice an error means that value is not possible. Doesn't exist in the domain. Okay, you can see their graph here as well. Now, let's try f divided by g of x, and we'll update the window accordingly. So I'm going to go back to y. This time, I'm going to do f divided by g of x. So I'm going to do alpha y1, alpha f4, divided by y2. Oops. Divided by y2. So now I have f of x over g of x. I'm going to do it on the specific zoom of 5 to 15 and 0 to 0.016. So if I go window, I'm going to graph it on 5 to 15. And then I'm going to go 0 to 0.016. I'm going to hit graph, and I have graphed the composition of the function here. So this is f over g of x that I've used my calculator to graph instead of having to graph it by hand or to try to do the manipulation of functions and simplification. It's taking care of a lot of the work for me. Okay, like I said, you can see the same graph that they have here. Now, let's say we actually want to compute some values. Say we want to compute f of g of -3. We could actually go to the blank screen once we have them entered. You do have to have them entered in here. You have to have them entered in y1 and y2. Okay, you have to have your original functions entered. If you have those original functions entered, if you go to your blank screen, all I did was exit out of there. I went from here, I just went second quit, which brings me back to my blank screen. If I want to, say, find f of g of -3, this is essentially the same thing as finding y1 of y2 of -3, because remember, we let f be y1, we let g be y2. So all I have to do is go in on my calculator here, type alpha f4 y1, put a parentheses down, insert my y2, another parentheses, and I'm trying to find it of 3. Okay, if I do that, I can tell, or sorry, -3. Oops. -3. Made a typo. So let's adjust this in the calculator. Okay, I'm going to copy it down. I'm going to insert the negative because it's supposed to be -3. And you can tell that it updates it. My result here is 3. So y1 of y2 of -3 renders a result of 3, which is the same thing they have here. I can also do the same thing, say if I want to compute g of f of 9. That's the same thing as y2 of y1 of 9. Let's see if we can enter that and get the correct answer. y2 of y1 of 9. y2 of y1 of 9. It gives me the answer here of 4. Okay, just like it said it would. Now, essentially what you're saving yourself here is if I had to find f, well, let's start with just the first simple one here. If I had to find f of g of -3, and I was doing it by hand, okay, then f of g of -3 here would be f of g of -3, which means that I would need to take my f of x function and plug my g of x function in with 3 in it. So I'd have to take the square root x minus 5, but instead of x, I'm going to plug in 2x squared minus 4. Okay. And then I have to also keep the -5 in there. Put the -3 in for the x, because that's what we're inputting in for x here. I would have to simplify this down. So it would look like 3 squared is 9, so 2 times 9. -4 and -5 give me a -9. 2 times 9 is 18. 18 minus 9 is 9. So I'm looking at the square root of 9, which is 3. That's how they get the 3. The calculator does it for you. Same thing would have to happen over here if I was to input the 9. It would just have to work the other way. I would have to do 2 times the square root of 9 minus 5 squared minus 4. Essentially putting in the 9 for my x here, putting my f of x function into my g of x function. 9 minus 5 is 4. Square root of 4 squared is 4. You're looking at 2 times 4 minus 4, which should give you 8 minus 4, which is 4. So you can do these by hand, or sorry, -4. Where did I mess up? No, it's +4. Sorry. That is correct. Okay. But you can do these by hand. You can use the calculator to help you compute either way. But that pretty much completes the lecture for today. If you have any questions, don't hesitate to reach out and ask. Other than that, I'll see y'all next time.